Hey everyone, welcome to Lesson 4, Unit 6, Lesson 4, Lecture 4 in Chem 1111. This will be, I hope, our last lesson of new material, but we'll see. Okay, so I'm in our textbook. The first little bit's going to be a bit of a review actually, page 289, where we're looking at covalent bond properties, and we'll also have the PowerPoint slides at their ready here. So bond angles, we can say that there you go, lone pair repulsion is greater than lone pair bond pair is greater than bond pair. So here we have on the right something like PCl4 plus, almost like ammonium. So this is a tetrahedral molecule, and the chlorine, phosphorus, chlorine angles are all 109.5 degrees. Okay, now if we go to PCl5, we have the equatorial region where the chlorine, phosphorus, chlorine angles are 120. Three of them making up 360, and then we also have an angle between an axial chlorine and an equatorial chlorine of 90 degrees. Okay, so it's nice to have the symmetry, and we saw when there's lone pairs that symmetry is broken a little bit. So for an ammonia, the H and H angle is 107, and water it's 104.5. And we mentioned that the lone pairs spread out over more space and squeeze in the bond pairs, so the bond angles get smaller. Okay, so here's sulfur tetrafluoride, and this is a seesaw, right? You can see that. So you see how the angles aren't 90 anymore, it's 86.8, and instead of 120, it's squeezed down a lot in this case to 101.5. So that's how that works. And chlorine trifluoride, the angles are squeezed down again. Here's water squeezed down to 104. Here's the two resonance structures of ozone, and you see there's a lone pair there, so the bond angles are less than 120. They're bent off of 120 to just 117 degrees. Again, we looked at that before, so I'm not going to redo every little bit about it. Okay, so here's something that may be new for some of you, the dipole moments of molecules. So molecular dipole moments, this is on page 290, and they're called mu molecule. So a molecular dipole, or dipole moment, I like to just say molecular dipole, is going to be the vector sum of all the bonds dipole. So you add up all the bond dipoles vectorially, and that's the molecular dipole. If you have a molecular dipole, then you have a polar molecule. You have a positive end to the molecule and a negative end. If you add up vectorially all the bond dipoles and they all cancel out, so the molecular dipole is 0, then you have a non-polar molecule. We care if a molecule is polar or non-polar. It's involved with hydrogen bonding, intermolecular forces, solubility, properties in electric fields for capacitors, biochemistry. Polarity is important. Okay, and we learned before from electronegativity differences that the greater the electronegativity difference between two atoms participating in a bond, the greater the polarity of that bond. So now we take a few of these bonds and we add them together. Okay, you can talk about the actual values. We aren't going to really calculate the values. The units are debye, but it is has to do with the transfer of charge times the distance between the two atoms, or the center of atoms, center of masses in a molecule. But we won't actually calculate that number. So this is going to be a bit more qualitative. We see here that hydrogen fluoride, it has a bond dipole which is polar. Well, the molecular dipole is polar as well, because the molecule is just the one bond, right? So if I put an applied electric field, then the negative end of the molecule, which is the fluorine, partial negative end, is going to be attracted to the positive plate. So you're going to get this general alignment where if there's no applied electric field, they're all just jostling about. So that's one example. Okay. So now let's look at some examples. And this is on page 291. We see here with some hydrides, halohydrides, hydrogen chloride, hydrogen bromide, hydrogen iodide. The greater the electronegativity difference, the greater the polarity, which means the greater the bond dipole. So we didn't calculate the number, but just look at the number. Because chlorine is more electronegative than bromine, which in turn is more electronegative than iodine. The bond dipole, they're all polar molecules. They all have electronegativity differences more than 0. The bond dipole is equal to the molecular dipole for any diatomic molecule, and it is larger for HCl than HBr than HI. So those dipoles, molecular dipoles, depend on the difference in electronegativities, and they also depend on the shape. A molecule can have polar bonds but no dipole moment if the symmetry is such that the polar bond dipoles cancel each other out. Sometimes that happens, sometimes that doesn't. So here in figure 6.28, snuck on the margin here, if you have carbon dioxide, you do have two polar bonds, right? The oxygen is more polar than the carbon, so that's the partial negative. This oxygen is more polar than the carbon, so that's the partial negative. So you have two bond dipoles, but they cancel each other out, so the mu of the molecule is going to be 0 dBs. Okay, so the dipole moments cancel out, and it's going to be 0. For this molecule here, you have H2O, and so the oxygen is the negative end, and we're going to have the oxygen withdraws charge from the hydrogen partially, and this is a bent molecule. All bent molecules are polar because you see that even though the horizontal displacements, if I decide to break that down and break this one down, right, into horizontals and verticals, the horizontals cancel, but the verticals add together. So a bent molecular geometry, whether bent off 109 or even off of 120, any bent molecular geometry is going to be a polar molecule. There's no atoms up here that are going to fight against the vertical pull. So we say that the oxygen is the negative end of the molecule, and between the two hydrogens is the positive end of the molecule. So water is a polar molecule. It has a dipole moment that is greater than 0. Okay? And we're going to just keep doing some more examples. That was bent. Let me just sneak one in here that wasn't mentioned. SO2, just that's just four. Not those ones. So here, it's trigonoplanar molecular geometry bent off of 120. Molecular geometry, and you have, so it's bent, oxygen is more electronegative than sulfur, so you have two bond dipoles, and overall you do have a molecular dipole. So whether it's bent off of 120 or bent off of 109, it's going to be a polar molecule. Another thing I guess I should have said right at the top, something like hydrogen is nonpolar, nitrogen is nonpolar, right? Homonuclear diatomic molecules are nonpolar, heteronuclear diatomic molecules are polar. If you have a triatomic molecule, well, if they're collinear and you have the same ligand on either side, it's nonpolar. If we had something like this, I guess we should say this one. Okay, this is The carbon and sulfur are very close to each other. You might have a very slight pull one way or the other, but then the oxygen is much more electronegative than the carbon is. So you don't get the vectors canceling out completely. So the ligands are different. In a linear triatomic molecule, the molecule is polar. And then we said if you have a bent molecule, triatomic, whether it's bent off of 109 or bent off of 120, it is still polar. Okay, now if I go to more than 3 atoms, I can look at phosphorus pentachloride. That is going to be a nonpolar molecule, phosphorus pentachloride, right? You're going to have chlorine above and below, so chlorine's more electronegative than phosphorus, so those bond dipoles cancel, and then you have these trigonal planar in the center, but they're all 120 degrees to each other, so it's like 3 people moving a piano, and the piano, represented by P, is on casters, and they're all of the same strength, and they all pull at the same time. The phosphorus doesn't go anywhere, right? So all the ligands are the same in this trigonal planar region, therefore this is going to be a nonpolar molecule. If I just looked at something like BF3, get a little bit simpler here, and you may remember this from last year, the fluorines are all 120 degrees to each other, so they're all pulling at the same time with the same strength, and this would be a nonpolar molecule even though you have 3 polar covalent bonds. If you're good in vectors, you can add 1, but we have 3 vectors here, right? So I could just slide a vector up and then back down, and you're back to where you started from, right? Or I can do trigonometry and resolve it into right angles, and you see that the horizontal components cancel out, and the 2 vertical components double down and cancel out with the 1 pointed up. Okay? So if I change the ligand, if I change even 1 ligand, here's a chlorine, here's 2 fluorines, so now not all the ligands are the same, not all the pools of electrons are the same, so this would become a polar molecule. Okay, so you have to look at what kinds of ligands there are and the symmetry associated with them. Here I got 5 atoms altogether, a central atom, and then 4 around it. This is carbon tetrachloride. It is a nonpolar molecule. Tetrahedral molecular geometries are nonpolar if and only if the ligands are of the same kind, and they are here. They're all chlorines. And I could draw the vectors, bond dipoles. I got 1 here and here. Then I got 1 going out and 1 going back. And those are all going to cancel out. You'll get cancellation. So the whole thing is going to cancel out. If you have a molecular model with you, you can see that. If I change even 1 of those, or 2, or 3, or 4, then it becomes polar. So what I've done here in this one is I've knocked out the top chlorine and put a hydrogen there, and so now it doesn't pull up, actually it doesn't pull up at all. Carbon's a bit more electronegative than hydrogen, so everything's pulling down, so we have a bond dipole directed downwards, a value of 1.04 debye. Okay. Now, seesaw molecules are basically taking away one of these ligands on the equatorial plane in a trigonal bipyramid and making it a lone pair. So you've reduced the symmetry somewhat, and now you don't have that perfect cancellation in the trigonal planar area of the equatorial region. So all seesaws, whether you have the same ligands or different, are polar. Okay, so all seesaws are polar. ClF3 is T-shaped, so that's like taking away 2 of these ligands, and all T-shapes are polar, regardless whether the ligands are the same or different. Again, being because you don't have atoms pulling the electron density the other way to cancel things out. Pyramidal molecules, okay, because we didn't look at that one yet. Well, we have, but in this context. So a pyramidal molecule, here's ammonia, classic. And there's my lone pair. So I don't have any atom pulling up. So this one is going to be a bond. We have the 3 bond dipoles all directed towards the nitrogen, and they're going to add up, and there's nothing directed down. There's no atom directed down countering the pull up of electrons. So any pyramidal molecular geometry, trigonal pyramidal molecular geometry, is polar. In fact, any square pyramidal molecular geometry is polar as well, again, because you don't have the complete cancellation. Okay, so with the octahedron SF6, that it would be nonpolar, everything would cancel out, but if all the bond dipoles would cancel out. If I change one ligand, well, now here, this one's actually quite interesting. If I have SF6, what if I have like something like SF4Cl2? So I could have a Cl and a Cl here, and then I could have Fs, 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 and Fs. And now this would be nonpolar because the Cl's would cancel and the F's would cancel in that square planar region of the octahedron. So you just have to look at the symmetry and figure things out. If it's a square pyramid, it's always going to be polar. Square planar, again, you have to look at the symmetry of the ligands to see how that works out. Another trigonal bipyramid, I3-, you'd have to look, that's actually going to be nonpolar because all the lone pairs cancel out. So it's a linear molecular geometry with lone pairs around the central atom, but all the bond dipoles cancel out, so it is a nonpolar molecule. Does either ClF5 or XeF4 have a dipole moment? So here's the drawings. This is example 617, and we see that the ClF5 is polar. It's a square pyramid. There's no fluorine at the bottom counteracting this pull up, so this is a polar molecule. XeF4 is, I'm not drawing in the lone pairs, I'm just drawing in the ligands in the central atom. This is square planar, and the bond dipoles cancel out, so this one is nonpolar. Okay, steric number is 6 for both of them. ClF5 square pyramid, XeF4 square planar, and you see the cancellations happening. And ethane, okay, that's getting a bit fancier there, but ethane would be nonpolar because each inner atom, each carbon's, yes, the electrons should have a vector in each of those subparts towards the carbon, but those would cancel each other out. Ethanol is polar because you don't have that cancellation completely. So that was the business about polar versus nonpolar, and we can just summarize the last little thing here. Bond length is another thing about we were discussing about geometries, and the story is the stronger the bond, the more electron glue is what we call it is, the shorter is the bond. Okay, so the stronger the bond, the shorter the bond, and we also can look at atomic radii, so we can see things like, on average, an OH single bond is going to be shorter than an SH single bond because sulfur is bigger than oxygen. Phosphorus is bigger than nitrogen. Silicon is bigger than carbon, is bigger than hydrogen. Bromine is bigger than chlorine. you get the idea, right? And going across, you see the atoms get smaller. Nitrogen is bigger than oxygen, is bigger than fluorine, so the bond lengths get smaller. I can even start at carbon. Okay, so that's one concept behind it, and you can see it repeats in other rows in the periodic table. There'll always be a few little exceptions here and there. So again, these are average bond lengths, and then I wanted to talk a bit about multiple bonds here, but you have to look at the same two participating atoms. So I can have a carbon-carbon single bond is 154, carbon-carbon double bond is 133. So this double bond is stronger than the single bond. If it's stronger, there's more glue there, so it can stick together more tightly. I like to talk about the electron glue. Now, I didn't make that up. I remember some professors telling me that that's a good way to discuss electron density. Around 40 years ago, they told me that. And where's a carbon-carbon triple bond? I don't see one here. I think this should be carbon-carbon triple bond. Yeah. I'll go down here. Multiple bonds. Yeah, those should be triple bonds at the bottom. They left with double bonds. Triple, triple, triple. Okay, so triple bonds are shorter than double bonds, which are shorter than single bonds. Okay. So let's see. Okay, some of the stuff is a bit, sometimes the book tries to push too much stuff around there. So let's just summarize some factors affecting bond lengths. The smaller the atoms, the shorter the bond. The higher the bond multiplicity, that means it is a single, a double, or triple bond, the shorter bond. The higher the effective nuclear charges, the shorter the bond. Okay, that's another part to it. And the larger the electronegativity difference, the shorter the bond. Okay, because they're getting more attraction, so they're getting closer to each other. So I2 has a longer bond than Br2, well, because iodine is bigger than bromine. Cn bonds are shorter than Cc bonds. Well, you got a bit of an electronegativity difference here. So also nitrogen has a smaller radius. So both of those are reasons why the Cn bond is shorter than the Cc bond. Hc bonds are shorter than Co. Really? Whoa, hydrogen is smaller than oxygen, but oxygen is more electronegative. Well, the size of the hydrogen orbital is more an important factor. Okay, so than the multiple bonding. Formaldehyde, the C double bond O is longer than the CO triple bond. Carbon-oxygen bond is longer, okay, because it is just a double bond. A triple bond's got more glue, and it makes it shorter. Okay, and you can try the practice exercise on your own. I've already mentioned the bond energy. Bond energy increases as more electrons are shared. There's the glue. And it also increases as the electronegativity difference increases. Polar bonds gain stability from the electrical attraction between the negative and positive fractional charges or partial charges around the bonded atoms. Bonds between oxygen and other second row elements exemplify this trend. So OO, the electronegativity difference is 0, so it's a nonpolar bond. Bond energy is 145 to break it. ON, now we have a bit of a electronegativity difference, so the bond energy is more. OC, even more of an electronegativity difference, the bond energy is 360. Bond energy decreases as the bonds get longer, right? HI is a longer bond than HBr, is a longer bond than HCl, is a longer bond than HF, so the bond energy gets smaller. For larger atoms, the electron density of a bond is spread over a wider region. This decreases the net attraction between the electrons and the nuclei, and so that's how that happens. Okay, it's table 6.2 we've looked at before, and section exercises you can try on your own. It's a good idea. You should do that. Okay, so try section exercises 6.51, 6.52, and 6.53, and tell me if you get stuck on any of that, or talk with your colleagues about it. And then our famous visual summary. So we had the overview of bonding, covalent bonding, and then we talked about drawing Lewis diagrams, formal charges, molecular shapes. There's a whole bunch of molecular shapes. Someone should make earrings about these, or candies, right? You know, they have like Sour Patch Kids or Cherry Blasters. We'll make them of Vesper Yummies. No, that doesn't work. Okay, you guys come up with a better one. Then properties of covalent bonds. We looked at bond lengths, bond angle, dipoles, dipole moment if you want, and then we get into the exercises associated with the chapter. Let's see here if there's anything that the PowerPoint slides can tell us that we haven't already seen, and I'm going to switch it to the projector mode. There's some bond dipoles. There's the question: bond length, bond energy, average bond lengths. What affects bond lengths? Effects. Yeah. And we mentioned those. Looked at that example. Bond energy. Looked at that. And there's our great table. And there's our visual summary. Okay. So that's it for this chapter, for this lesson anyways.